A CI container cloning a monorepo OOM-kills after 10 minutes. The culprit? Thousands of Packfiles from fetch without gc. Let's break down Git internals. Objects, trees, blobs, and the DAG, how it works, and the exact mistake behind that failure. Git is a content-addressable file system. It stores data as objects identified by SHA-1 hashes. The 4 object types, blob, tree, commit, and tag, form a directed acyclic graph that represents your project history. When you run git add, Git creates a blob object for each file. The blob stores the file content, not the file name. File names are stored in tree objects. This separation is critical. Renaming a file doesn't change its blob, only the tree that references it. Let's create a test repo and explore the objects. We'll initialize a repo, add a file, and then inspect the blob, tree, and commit objects using git catfile and git lstree. A blob is a binary large object. It stores the raw content of a file. Blobs are immutable. Once created, they never change. If you modify a file and restage it, Git creates a new blob. The old blob remains until garbage collected. We can create a blob manually using git hashObject w. Notice that 2 files with identical content produce the same blob hash. That's deduplication in action. A tree object represents a directory. It contains entries with mode, name, and a reference to a blob or subtree. Trees are also immutable. When you change a file, Git creates a new tree for that directory and recursively for parents, reusing unchanged subtrees. Let's create a nested directory structure and inspect the trees. Git lstree, rhead shows the recursive listing, and git catfile p on the tree hash shows the raw tree object. A commit object ties everything together. It contains a tree hash, 0 or more parent commit hashes, author committer info, timestamp, and a message. The parent pointers form the DAG. A linear history is a chain with 1 parent each. A merge commit has 2 or more. Let's create a branch, make commits, and merge to see the DAG. Git log graph 1line all shows the branching structure, and git catfile p on the merge commit shows its 2 parents. The DAG is what makes Git powerful. Branching is just creating a pointer to a commit. Merging creates a commit with 2 parents. Rebasing rewrites history by creating new commits with new parent pointers. The old commits become unreachable and eventually garbage collected. We can inspect parent relationships with git revlist parents, find dangling commits with git fsck lost found, and list all objects reachable from head. This helps understand the DAG structure. Loose objects waste space and a nodes. Git packs objects into packfiles, a single file containing multiple objects, compressed with delta encoding. Delta encoding stores a base object and a series of differences. This is why Git gc can drastically reduce repo size. Let's count loose objects, run Git gc, and see how packfiles reduce the count. Then inspect packfile contents with git verifypack to see the delta chains. Refs are pointers to commits. Branches, tags, and head are refs stored in. Git refs, the reflog, records every movement of head and branch refs. It's your safety net. Even if you lose a commit from the DAG, the reflog keeps it alive for 90 days by default. Let's simulate a lost commit with git reset hardhead ~1. The reflog shows the old head. We can recover the commit by creating a branch from the hash found in reflog. This is the same issue we highlighted at the start. Here's exactly why that happened. The CI container ran frequent git fetch without git gc, accumulating thousands of packfiles. During clone, Git tried to load all packfile indexes into memory, exhausting the 4 GB limit. The core delta base cache limit default, 96 MB, was also too low for the delta chain depth. The root cause is that frequent git fetch without gc forced Git to load all packfile indexes into memory, exhausting the container limit. The misconfiguration was the absence of fetch_unpack limit and gc settings, causing Git to keep many packfiles instead of unpacking and repacking them. The fix involved setting core delta base cache limit 256 M to increase the delta cache, running Git gc aggressive on the remote to consolidate packfiles, using shallow clones with depth equals 1 in CI to avoid fetching full history, and setting fetch unpack limit equals 1 to prevent creating new packfiles on every fetch. This resolved the OOM and prevented recurrence. This is the incident from the hook. Frequent git fetch without git gc caused thousands of packfiles to accumulate. During clone, all pack indexes were loaded into memory, causing OOM. The fix is to run periodic gc and use shallow clones in CI. Large blobs like binaries or datasets bloat your repo. They never get deduplicated because content changes. Use git lfs or git annex for large files. A 100 MB binary committed once stays forever. Even if deleted in later commits, it lives in history. Git doesn't store rename metadata. It detects renames by comparing tree contents. 2 commits with similar trees but different file names trigger rename detection. That's why git log follow is expensive. It has to walk the DAG and compare trees. Don't use git commit allow empty to create a commit without changes. It still creates a commit object with the same tree as parent. It's useless and pollutes history. Use git tag instead for markers. Running git gc on a bare repo with many concurrent fetches can cause corruption. Git 2+ has gc, auto-detach to run in background, but on shared file systems like NFS, it's risky. Always run git gc during maintenance windows. Don't set gc, reflogExpire equals never for critical repos, that's dangerous. Instead, set gc, reflogExpire equals 90 days and gc, reflogExpire unreachable equals 30 days. That gives you 90 days to recover any commit, even if unreachable. Git now uses SHA 256 by default for new repositories, since Git 2.29+. The article's examples use SHA 1, which is still supported but considered weaker. For new projects, consider initializing with Git init object format equals SHA 256 to future-proof against collision attacks. The article mentions creating blobs manually, but doesn't show how to create a tree or commit manually. This snippet demonstrates constructing a tree and commit from scratch, useful for recovery or scripting. Running git gc on a bare repo with concurrent fetches can cause corruption on shared file systems, e.g., NFS. Git 2+ has gc, auto-detach to run in background, but it's still risky. Always schedule gc during maintenance windows and consider using git maintenance, Git 2.3+, for safer incremental optimization. Here's a debugging guide for common Git object issues. Run git fsck full to identify corrupt or missing objects. If a loose object is corrupt, try recovering from a packfile with git unpack objects. If a packfile is corrupt, delete it and refetch. Use revlist and catfile to find large blobs that bloat the repo. Let's run through some common interview questions. How does Git handle merge conflicts internally? No special objects. Uses three-way merge and writes conflict markers to working tree. When to use Git gc aggressive vs Git repack, AD. GC aggressive for deep optimization, repack for regular maintenance. What happens to DAG on forcepush after rebase? Old commits become unreachable, eventually GC'd, can recover from reflog. And a few frequently asked questions. What is a blob? Raw file content stored by SHA-1 hash, no metadata. Difference between tree and commit? Tree is directory snapshot. Commit adds metadata and parent pointers. Can I recover a commit after git reset hard? Yes, use reflog to find hash and create a branch. To recap, Git stores objects by SHA-1 hash, enabling deduplication. The DAG of commits is the backbone of history. Packfiles with delta compression make Git efficient for large repos, and the reflog is your safety net for recovering lost commits. Ready to go deeper? Up next, conventional commits. Standardized commit messages, then git blame. Find who changed what and when, then git worktree. Work on multiple branches simultaneously. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.